So the next session is on rendering, and I'm not going to introduce myself because I was just talked a lot. So the first paper in this session is real-time Markov chain path guiding for global illumination and signal scattering. And Lucas is going to give the presentation, so take it away.
Thank you for the introduction. So yeah, traditionally we were using rasterization to generate images in real time. Now with recent hardware advances, we have started to move to ray tracing or even path tracing for their consistent look, physically accurate lighting framework, which is why it's used in the VFX industry for years, and also to get rid of all the workarounds which are required in rasterization. Now, why isn't path tracing the default? Like, the image here on the left looks a lot better, right? So the reason is we have still a very limited ray budget in real time. This results in noisy images, like here on the left, when doing naive path tracing. We can improve that, for example, by allocating the rays such that most information about the scene is extracted and the noise is reduced. And we can also use denoising, for example, using SIGGRAPH. However, denoising can only do so much if the images look like this. So we're focusing on the first here. And in fact, our algorithm that I'm presenting now can produce path trace images like this one on the right in real time with the same number of rays, which then can be denoised more easily. And we can even do that in real time and dynamic scenes. This can be seen in this demo here. Okay, to understand where the noise is coming from in the first place, let's recap how path trace lighting is computed. The render equation is used to describe the light transport in the scene. And for a surface point C, the emitted light in direction omega is the emitted light at C and the reflected light, which is expressed here through this integral in green. Now this integral is difficult to compute due to its recursiveness and visibility that is required for the incident light. For that reason, we're using a Monte Carlo approach. We take samples of the integrand by tracing paths in the scene according to some probability density P. By dividing the probability density and taking the mean, we then obtain an estimate of the integral. The approximation error or variance manifests itself as the noise in the final image. And we can reduce that by increasing the number of samples, but actually we can't because our ray budget is limited, or by selecting a good probability density that is close to F. For example, we can sample the BRDF, FR, which describe the material properties, and we call that importance sampling. Now, the issue is, the image I showed earlier already used importance sampling of the BRDF, so that didn't really help. And to really reduce the variance to such an amount that the images get usable, we need an approach which also takes into account the incident light. And one such approach is path guiding. Path guiding usually learns the light distribution in caches, which are placed in the scene. And most approaches just differ in the data structure that is used to manage the caches or to represent incident lighting. However, most of the existing methods are for offline. And thus, most of them have limitations in our case. For example, they're non-adaptive, they require expensive fitting, have dedicated learning phases, or are just unpractical for GPUs. That is what we try to attempt to overcome with Markov chain path guiding. We present a lightweight path guiding algorithm for multi-bounce indirect light in real time, and we make low assumptions on the scene representation, making it easy to integrate in engines. Our estimators are unbiased and quickly readapt the guiding distribution, also in highly dynamic environments, without requiring additional rays. Also, it extends naturally to guide single scattering events in participating media. At the core, we represent the incident light using a von Mises-Fischer distribution. Because it is suited for directional data, it has an efficient online fitting procedure, and it is simple and compact, requiring only 4 floats. Now, a single lobe isn't capable of representing a complex light distribution. But to increase expressiveness, we can combine multiple VMFs or techniques in a mixture model. Now, instead of selecting a discrete amount of lobes, we can also use a continuous mixture. And we can use a probability density to select the techniques. That is where the sum gets an integral. And that's what we're using. In our case, we want to select the techniques using a stochastic Markov chain process. And to evaluate the model, we use stochastic multiple importance sampling. Now, the reason is when we look at the formula for SMIS, there isn't actually the selection probability in the formula. And this gives us a lot of freedom in the design of the selection procedure itself. Previous work already used this concept to store von Mises-Fisher parameters per pixel, which are then controlled by Markov chain and exchanged with neighbors. Note, this is in contrast to raster-based methods where the light samples themselves are exchanged between pixels. Now here the obvious issues are only information about the first visible surface is available, and the mixture has to be relearned every time the camera moves. Also, only the first interaction can be guided, and so no indirect illumination is supported. For that reason, we use a hash grid in real space, where we run a Markov chain per hash grid vertex. Here, each vertex stores a Markov chain state consisting, for example, a mean position and mean cosine, from which we can reconstruct the von Mises-Fisher parameters more robustly after sharing. We also store a weight for the Markov chain and for a sampling step, which is part of the guiding procedure I present now. This procedure runs for each ray intersection, and for better understanding, I split it into 4 steps here. A resampling step, where we select states from the grid, the sampling and tracing of the selected lobe, the estimation step, where we compute the SMIS estimator, and finally, the Markov chain transition and update. In the first step, we select a few grid vertices, stochastically based on their interpolation weight. We then select one of the lobes using weighted reservoir sampling. As mentioned previously, we now have to reconstruct the von Mises-Fisher parameters. We then use the selected lobe to sample a direction and trace array. Using this information, we can compute the SMI estimator for the path throughput. However, for the path guiding update, we also need an estimate of the incident light. Now, we do not want to backtrack paths because that gives a lot of register pressure. And also we want to stabilize the incident lighting estimate a bit. For that reason, we're using an irradiance cache. And we are reading the irradiance cache here in this step, but only if the surface was not emitting. We can do that because we assume that after the first bounce, light already has diffused a bit. So it is smoother anyway. Now we can estimate the incident radiance for maximum likelihood estimation in the next step. As I said, the next step is maximum likelihood estimation to adapt the lobe. And then we perform a Markov chain Monte Carlo acceptance test, which decides whether we want to write back the new state into the grid. Again, we select the grid vertex stochastically using the interpolation weight. Finally, we can also update the irradiance cache, which gives us like an infinite bounce estimate of the radiance transfer in the scene. The whole procedure results in a complex feedback loop, which is the reason why we have to use SMIS in the first place. The exchange with neighbors is done by sharing the grid vertices, so it's like naturally shared with neighbors. However, we want to use a high resolution of the grid to get high quality. At the same time, this slows down sharing. For this reason, we're not using one grid, but a multi-resolution hash grid, where we select a level randomly. And we select the base level based on the camera distance, so that the projected area on the screen remains roughly constant. Okay, now for single scattering, we also have to collect the contributions along the camera array. And for that, we can sample, for example, the transmittance in the medium. However, we tried also applying the same procedure for distance guiding and for some results. If you're interested, you can look in the code for that. Other than that, we only have to use the phase function instead of the BSDF, as the guiding method already operates on a spherical domain. For dynamic content, we can also improve the base method. For example, we can store the light velocity in the state to estimate its new position. We can read the grid at the position of the previous frame of the geometry to transport the information very efficiently to the new grid position. And finally, we use a heuristic to detect missing light sources without tracing additional rays. Otherwise, the MC-MC acceptance step might take a really long time to replace a state which has seen a pretty bright light source. Okay, I'm now presenting some results, and all were recorded on an AMD Radeon RX 7900 XTX. I show here our small Quake tech demo. We achieve around 60 FPS in most scenes with around 2 samples per pixel, with both indirect lighting and single scattering enabled. This is native Full HD. We also tested the first generation of ray tracing GPUs and were surprised, for example, a 2080 Ti can run the demo with around 30 FPS in most scenes. Also note that all results are without any sort of next event estimation or light sampling. That means we're just relying on the BSDF sampling and efficient sharing for light discovery. For direct light, we compared against the previous technique by Brandt and colleagues and Riester DI. And here at these equal time renders, we observed the advantages of a well-spaced data structure, which has less artifacting at the geometry edges and remains higher quality at very small geometric features where reuse is limited in the screen space techniques. This results in this scene in a lower error. Though we have to acknowledge, in this scene the guiding distribution is very simple, and we'll see a different case later. We also observe very quick convergence compared to the previous technique. And note, you have in the screen space technique by Brandt, you observe this every time you move the camera. In our case, you will see this at the first time a surface is visible, and in the 2 bounds on the right, you see this only once, the first time the scene loads, because the indirect rays already warm up the grid offside the camera. For single scattering, we also explored the viability for caustics in an offline scenario, but we were also surprised by the output in real time, which can be seen here on the right. Here in the offline scenario, 32 samples were needed for equal error with an 8,000 samples per pixel image, which uses phase function importance sampling. Note that this is using an anisotropic phase function. Okay, now onto some limitations. We observed increased variance in scenes with many lights, which we attribute to a very small SMIS set. This can be seen here as a darker appearance as the energy concentrates in the outlier pixels. And this is also something Riester does a lot better here. The second point is proximity bias, which leads to high variance at shadow borders. This is because we might share a state with a neighboring vertex, but from the new position, the light source might be occluded. Note that this bias is only in the guiding distribution, and the final image remains unbiased. Still, we had no issues with our implementation of SVGF. Yeah, we released our demo as a project on GitHub, so you can try the algorithm yourself. Thanks for listening.
Questions?
Great talk. So do you see some artifacts from hash collision? Because I noticed that you're using hash grid.
Yeah, that's right. So not really, but also if you use a too small grid, you start seeing blocking artifacting.
Yeah.
But in for surfaces in these scenes in Quake, you get away with 50 megabytes with just surfaces, and you need around 500 megabytes if you're using single scattering.
All right. Thank you.
Hello. I already went through what you were saying and how you used Markov's path guiding technique for your implementation. But I was wondering how do you determine the target for the light to go through, to guide your light through and go towards the target. I was wondering, how do you determine that target itself in your implementation? How do you determine a light has to be guided through? So I was wondering if you can clarify on that.
Okay, I hope I understand your question correctly. So first, we're just using VSDF sampling to get some information about the scene. And then the states start to learn where the light is coming from. And we then have an acceptance probability, which depends on, for example, the current sample, which, for example, if the PDF was slow because we didn't see it before, makes it really results in a high probability of accepting this sample and updating the lobe.
So on the follow-up, I saw the path tracer for your Quake demo. I was wondering how it would work in a more of a lower end system, let's say a 4060 or 4070. How do you think it would perform? I was curious.
Yeah, so we tried the 2080, and so I didn't try a 3070 or so, but I believe they're similar in ray tracing performance.
Okay, all right, thank you.
So in the slide, you also compare with the previous method, and then you show that your method is converging faster, right?
Yeah.
And then why was that? Maybe I missed.
Yeah, so they're just sharing with neighboring pixels, but since we started using the multi-resolution grid, that greatly accelerated the sharing. So you can imagine in the screen space approach, you see some seeds from where the distribution is spreading. But because our grid goes up to filling half of the screen, the information spreads so quickly you cannot see these seeds anymore.
All right, thank you.
Any other questions? Well, now let's thank our speaker once more. So the next talk in our session is joint denoising and upscaling via multi-branch and multi-scale feature network, and Sunye is going to present.
Thank you for the introduction. So, good morning. My name is Sunye Kim from AMD, and I'll be presenting the paper titled "Joint Denoising and Upscaling by a Multi-Branch, Multi-Scale Feature Network." So, in this work, our goal is to devise an efficient neural network architecture for joint denoising and resolution upscaling technique. So in this diagram, from the left side, given the noise, alias, and low resolution rendering from the rendering engine, our architecture generates denoised and upscaled frame as shown on the right side. So for this purpose, the neural network should extract the proper features for these two problems. And we also like to make it that lightweight enough for potential real-time performance. So let's look at the rendering pipeline with the ray tracing and denoiser in the pipeline. So when we use the upscaler in the pipeline, we have some amount of time saving with improved frame rate, as you can see here, because it allows to render the frame at lower resolution. And with our technique, we combine the denoiser and upscaler using a single neural network model. And then we have some advantage of sharing the trainable parameters from the neural network model. And then we save that in the feature space. And that gives us efficient filtering weight prediction for these two problems. So there has been some research work for denoising and upscaling, and even for joint denoising upscaling together. And there are a couple of software products in the industry, and they all showed great progresses in quality improvement. So the rightmost side one by Thomas et al., they introduced the single feature extraction network model and used multiple filtering stages to serve this problem jointly. And our work shares the same goal to Thomas et al.'s work, but our focus is more on efficient feature extraction network architecture. So here is a high-level view of our approach. The current frame at lower resolution is the input to our technique. And the current frame includes the noisy color buffer and G buffers like albedo, normal, roughness, and we have also depth and motion vector. And then the denoised and upscaled output is reused as a history data for the next frame generation. And in this work, we introduce a multi-branch, multi-scale feature extraction network model as our key contribution. For our neural network model, we consider the different characteristics in our input buffers. As you can see here on the top, the one sample per pixel color buffer is noisy as well as aliased. However, normally the G buffers we use to guide this noisy color buffer is that they are noise-free, but just aliased. So our key idea is that the feature extraction neural network model should be able to design with a different dedicated branch for these two different characteristics and to be handled well. And we propose our feature extraction model based on this idea. So to explain our multi-branch architecture, let me start with the UNet architecture first. So here I have a current frame information as well as history frame information as an input together. And for the current frame, I have noisy radiance as well as guiding information from the G buffer. And they all are concatenated together and then passed to the UNet as an input. And the UNet is structured with multiple layers of encoder and decoder layers. And the encoder layer comes with the downsampling operation to reduce the spatial resolution of the feature maps. And then the decoder side, it has the upsampling operation to reverse that spatial resolution. And then in the middle, we have a bottleneck block or bottleneck layer. This is the UNet general architecture. And we also have the skip connections from the encoder layers to the decoder layer to help the better contextual information preserved that lost actually during the downsampling operation in the encoder layers. And the last decoder layer outputs the feature map here F. But instead of using just a single feature map from the last decoder layer, we can consider the multi-scale features from each decoder layers. And these multi-scale features can be used for multi-scale filtering later. And this approach is already proved in many previous work. So we adopted this idea for our feature extraction network as well. And here, as I said, we are motivated by that different characteristics from our input buffers. So we introduce here multi-branch UNet architecture for our feature extraction model. As you see, we have radiance branch in orange color, and that is for noisy and earliest radiance buffer input. And we have guiding branch in green color, and we take the guiding buffers as an input for that branch. And in each layer, we have skip connection to help the radiance branch feature extraction from the guiding branch. And finally, we have 3 different scales of multi-scale features from each branch. So we have total 6 different feature map from this multi-branch, multi-scale architecture. As you see here, this multi-branch network model allows us to design a much smaller number of convolutional layers for guiding branch, as well as a smaller number of parameters, because they are noise-free and we don't really need a large or deep network architecture for that guiding branch. In addition, to make our feature extraction model to be more lightweight to compute, we used partial convolutions instead of a full convolution for most of the layer in the radiance branch, except the first encoder layer and the last decoder layer, as highlighted here in yellow blocks. These partial convolutions helps us to reduce the total amount of the convolution computation. That's basically the matrix multiplication, so that we can reduce our total computation, and finally, to be more lightweight network model. So this is our final proposed multi-branch, multi-scale feature extraction network for our denoising and joint upscaling technique. Now we have 6 different feature map from our feature extraction network model. Now we need to run our filtering stage. So the first step is to predict the filtering weight based on that features we learned from the feature extraction network model. The first step is to apply the upscaling filter to the low resolution noisy radiance as well as guiding albedo buffers. After that, we accumulate this upscaled radiance and guiding albedos with previously accumulated radiance and albedo buffers. Then that accumulated radiance goes to the multi-scale pyramidal denoising filtering after the albedo demodulation. Then the denoised output is blended with the previous output together to generate the final denoised and upscaled output. Now let me present our 2 evaluation study to highlight the benefit of our multi-branch feature extraction network model. First, here I compare the result using our multi-branch network model versus single-branch UNet feature extraction. We see some marginal improvement in the most of the quality matrices, as you can see here. But particularly, we see much better visual quality in this highlighted area with the shadow. And for this comparison, we set the similar amount of trainable parameters for the single branch UNet architecture to be fair comparison. And also we compare here the partial convolutions with the full convolution inside the multi-branch, our multi-branch feature extraction network model. We see slightly dropped quality matrices as you see here, but the visual quality comparison and differences is not really noticeable here. So it's like a trade-off between the quality versus the benefit we get from this partial convolution to help the overall runtime performance. The benefit of using partial convolution is that we can have smaller number of trainable parameters. For example, here we see 38% smaller trainable number of trainable parameters using partial convolutions, as well as we see 18% lower compute requirement when we use the partial convolution. And now let me present some results. For denoising and upscaling comparison, we have two baselines. First is the joint denoising and upscaling technique by Thomas et al. 2022. We implemented this technique from our side and also trained that model with our same dataset. And second is the optics denoiser from the SDK. It has 2x resolution upscaling option, so we used that built-in option to have denoised and upscaled output. So here is a result. From the left, we show the input 1 sample per pixel 1080p resolution. And in the middle, we have our result denoised and upscaled to 4K. And reference ground truth was rendered with the 8K samples per pixel at 4K. And we have two highlighted area to compare with other techniques. As you can see here, our result shows better details in this textured area compared to other two techniques. And here we show also the two quality matrices with the SSIM and LPIPs, and those numbers shows better with our result as well. And it's worth to note here, this is from the test scene, so we don't include this scene into our training at all. And here is another test scene. We compare. As you also see, our result shows better fine details in this complex area with the small font and the highlight and the geometry details compared to other two techniques. And bistro scene comparison, we compare here the thin geometry in far distance. In our result, we see better details from that geometry and better glossy reflection on the car object and also better texture details. Here is a video result from our work. It's denoised and upscaled to 4K. This is for temporal stability comparison. And with the low resolution input on the left top, that's rendered at 1080p, and we are denoising and upscaling. And here is a comparison with other two techniques, as well as the reference ground truth on the bottom right. And here we show the FOB BDP quality metric as a temporal stability matrix comparison. Right, and our feature extraction network can also support the denoising only problem. In that case, we can set the upscaling factor to be 1x. So here, we are comparing the denoising only case with 3 different baselines. The first is the optics denoiser from the FDK, and second is open image denoiser, and the last one is a recent research paper using transformer-based attention block in it. So we trained that research model from our training data set as well. Here is a comparison from Bistro scene. We highlighted 2 areas with high frequency details, one from the word texture, the other is from the tree. And as you can see here, our result shows better details in the tree, complex geometry area, as well as the fine details on the high frequency texture. Regarding the complexity, because we want to have this to be potentially real-time performance support. So using our feature extraction model based on the multi-branch and multi-scale architecture, we currently see much smaller number of trainable parameters compared to the previous work for joint denoising and upscaling by Thomas et al. And as well as we see G-flops for the compute requirement. At this time, we see similar amount of the G-flops compared to the previous work. But as I presented, we have better visual quality result compared to that work. We still have some limitations from our technique. For example, for highly reflective and transparent object, as you can see here in this image example, our quality is not quite to that reference ground truth reflection quality. The reason is that there is no valid information in our input or guiding buffer to represent this information at all. So to better handle this case, extending our guiding buffer with more information for this, for example, the secondary heat information in guiding or as a separated information would be useful to improve this reflection quality. And we leave that as our future work. And second is that at this time, we assumed all the post-processing effects like volumetric fog, particles, and the depth of field are after our technique. So it will be also interesting future work if we can include some of this effect in our input buffers or the guiding buffers. That actually will be another idea for the future work. Okay, come to the conclusion. We presented a joint neural denoising and upscaling technique with the multi-branch, multi-scale feature extraction network architecture. That is motivated the idea of different characteristics in the multiple input buffers. And also we demonstrated with high quality results as well as reasonable temporal stability compared to other previous research. That's it. Thank you.
Questions? Okay.
Hello. I just have a question. You mentioned the limitations related to transparency and things. Did you also test with objects that have potentially missing or like incorrect motion vectors, such as scrolling textures or like TV screens inside a game that have color changing content that doesn't match the motion vectors?
Yeah, at this time, we don't include any transparent and high reflection information in our data set because, for example, as you said, we don't have a valid motion vector, even we don't have a valid color information backside of the transparent object or the reflected object. And that might be from the behind of the camera reflected on the object. So in that case, certainly we need something else to have for color as well as motion vector. But fortunately for this work, we don't have that data set.
Okay. Yeah, I was just going to say, because in production use cases, it's usually really important to have at least a buffer that you can pass in to say, hey, I know this section of the screen is garbage. Don't use temporal samples here.
That's right. Yeah.
Thank you.
On one of your last slides, I think it was 27 or 26, you showed that your model has significantly less parameters than the competition, though it still requires slightly more gigaflops in terms of computation. I just want to understand why. Is it because it's more connected?
Maybe you are talking about this slide?
We can't.
Oh, we don't have slide? Okay.
Yeah, this one.
Okay. Can you say it again?
Yeah, so I'm not in machine learning, so I just want to understand. You have significantly less parameters to learn, yet the models actually require slightly more computation. I just want to know why.
Oh, okay. I got it. So overall, the computation-wise, it's similar, but I believe the reason why we have this much smaller amount of trainable parameter is that explain how we are efficiently learning the features from the input buffers. So we might not need really bunch of big parameter size at all to learn just the necessary feature from our input. And with this small amount of features, we still can have better or reasonable quality output as we expected. And we don't know, even if we have this 2.7 million parameters from other model, we cannot say that, okay, that all the parameters are really required to solve our problem. But with this chart, we can say that, oh yeah, we are efficiently learning the required features from our data, even if we have a similar amount of the compute to generate that. But still, to make this a similar amount of compute requirement, that's from the partial convolution we embraced to design our network model. So without that, we should have much higher number of compute than this one.
All right, that's clear. Thank you.
Hello again. I just have a question about performance. I don't know if there was anything on the slides about performance on current hardware.
So yeah, I didn't include that in this slide, but I have some comparison in our paper. At this time, we didn't have fully optimized the inference runtime at this time. So I only included PyTorch naive implementation comparison with the this Thomas et al.'s work, as well as I have some other numbers. That's from PyTorch implementation, any other optimizations at all. So you will see, as you see here, from similar amount of G-flops, we see similar millisecond time compared to this previous work at this time. But that's from 32-bit precision without any layer fusion, any other optimization at all. And also, we didn't include any other hardware optimization support for that number. So you can consider that as an initial number. And then by adding some different optimization technique, actually, you can imagine how that runtime will be in the future.
So in the video that you were showing there, is that just like the network running on the video and then the output? It's not like you don't have this in a real-time like shader implementation yet?
Oh, for the video I presented in this slide is from the offline generation, frame by frame, and then encoded for video.
Thank you.
All right, let's take further questions offline and thank our speaker one more time.
Thank you.
So the third talk of the session is EON, a practical energy preserving rough diffuse BRDF. And Stephen, is it you presenting? Is you presenting? Oh, both of us are presenting. All right. So there's multiple people presenting. It's going to be exciting.
As you wish. Okay, great. Hi, everyone. I'm Peter Kutz from Adobe, and this is Stephen Hill from Lucasfilm, and we will be presenting work that we co-authored with Jamie Portsmouth from Autodesk. And this is entitled EON, a practical energy-preserving rough diffuse BRDF. This is based on a JCGT paper, and it originally started when we were trying to find a suitable diffuse BRDF for the OpenPBR material specification. We're going to be presenting our new BRDF itself and a new important sampling technique. But before we do that, let's go through some fundamental background concepts and review those. So let's say you have a light source, you have some light hitting an opaque dielectric surface. Some of it will reflect specularly, and some of it will reflect diffusely in various directions, picking up the color of the object. So where does this diffuse reflection come from? The underlying mechanism of diffuse reflection is a little different for different types of materials, but in general it comes from small-scale local subsurface scattering. So if we look at all these different materials, you can see that, for example, for plastic, the subsurface scattering is coming from, for example, these pigment particles suspended in the plastic. In a leaf, it might be coming from scattering from cellular structures. In paper, it's coming from scattering from these fibers. But in computer graphics, generally, we don't simulate all these low-level details. We want to find a model that works well for all of these and can approximate the overall effect of light going in all directions. So typically, we assume in rendering that if you have a beam of light coming from whatever direction, regardless of the direction, the light is going to scatter off the surface in all directions randomly in a distribution that looks like this. And this is the Lambert or Lambertian BRDF. And it looks like this when you weight it by the cosine and plot it in polar coordinates. Very simple. But in 1994, Aron and Nair showed that if you take a photo reference, in this case a front-lit concrete vase, and you compare it to the Lambert BRDF, it doesn't match very well. It looks pretty bad. The Lambert BRDF has these dark edges in particular. So they actually introduced a new BRDF after showing that, surfaces aren't actually smooth like we assume in computer graphics most of the time. Surfaces like concrete are actually very rough, and that affects the appearance a lot, even for diffuse reflection. So instead of using a smooth surface like this, they actually used a rough surface like this. And each microfacet or each V cavity of this rough surface uses that same Lambert BRDF that we saw before. And if we take a closer look at one of these little V cavities, we can see what's going on here. So if we shine some light from the right side uniformly over this surface, you can see that more of the light lands on the left side. And that means that more of the light's going to reflect off the left side, and the left side is going to look brighter, right? So what that means is that if we look at this, say from the left side, we're going to see more of the darker microfacets. And if we look from the right side, we'll see more of the brighter microfacets. So this becomes a view-dependent diffuse BRDF. And in addition, Oren and Nair even simulated one bounce of diffuse interreflection among these microfacets. And when they rendered their new model, it actually matches the photographic reference much more closely. However, this model, it's really great, but it does make a number of assumptions and it has a number of limitations. For example, these Lambertian V-shaped surface cavities, that single inner reflection, which doesn't capture all of the energy. And in addition, the BRDF is a fitted approximation. They derived a bunch of complicated integrals and fitted some basis functions to them. Even the parameterization is a little complicated, and it's a lot of code to implement. So ultimately, this is an empirical BRDF that's not going to match the real world perfectly anyway. So if we can find a simpler energy-preserving alternative that retains the key visual characteristics, that would be a strong alternative, especially for cases like OpenPBR, where we already have energy conservation in other components like the translucency, the refraction. So we looked at a number of other existing variants of the Oren-Nair model. We show a bunch of these in the paper. We compared them with existing results from the past. We show renders in the paper as well, but here we just want to highlight a couple of them. One of them is called qualitative Oren-Nair, or QON. This is actually from that original same paper, but it's a simplified version. But it's very commonly used in practice. On the left, you can see direct illumination. On the right, you can see a white furnace render. That should just be one uniform gray color if it's preserving energy, but it's not. It's a little darker. It's losing a significant amount of energy. And in addition, there's this dark ring artifact that you can actually see in certain cases. This plot shows the energy loss for a variety of different roughnesses. We should just see one horizontal line along the top, but there's a lot of energy loss, and in certain configurations, there's even some energy gain. So it's actually adding energy to the scene. And then we looked at this another model that Fuji published in a blog post. And this model does a little better. It reduces the artifacts. It doesn't get quite as dark, but it still loses a lot of energy, especially at those high roughness values. And so that leads us to our new BRDF, which is we call the Energy Preserving Oren-Nair model, or EON. And basically, we formalized and validated Fuji's model, and we introduced a new multiple scattering component to preserve energy. And here's what ours looks like. It's a little brighter, and in the white furnace, it's perfectly passing. It just blends into the background. Mathematically, this is preserving and conserving energy, no energy lost or gained. So our new BRDF is it's structured like this. It's the sum of a single scattering component, which is based on that FON, that Fuji model that we just looked at, and a new multiple scattering component, which is mathematically derived and uses a structure like this, symmetrical structure, to preserve reciprocity in the renders. And we won't go into all the details of all these variables here, but you can see our paper for the full derivation and for the final values of all the variables here. But at a high level, what we're doing is forming our final BRDF from the sum of a single scattering component and a multiple scattering component. And this multiple scattering component, it's a little darker and more saturated because it assumes that at least two bounces have happened among the microfacets on the surface. And when you add that to the single scattering component, you get the final BRDF, which is a little brighter, conserves energy, a little boosted appearance. In the paper, we also provide GLSL code, including exact and approximate versions of one of the more expensive terms, this directional albedo term, to make this even more suitable for real-time applications. So we have some pretty accurate polynomial fits of this one expensive variable. And ultimately, our EON model has a lot of nice qualities. It matches the overall shape of the original Oren-Nayar model, that flat, rough appearance. It's energy preserving, reciprocal, closed form. It's compact, and it's intuitive to use. Now, if we compare a multiple scattering render against the popular QON model, we see ours is like much more brighter and more saturated. And if we look at a front lit render, similar to that concrete vase we saw earlier, this is where you can really tell the differences. So here's Lambert, the very commonly used model. You can see kind of still like dark edges. If we switch to the full Oren-Nayar model, you can see it gets much more flat. Similarly for the QON model, but both of those models are still fairly dark. Now, if we switch to our model, you can see it retains its same overall flat appearance, but it's actually much brighter. And comparing that to the Oren-Nayar model again, you can see the difference there. And if we compare it to Lambert, you'll see a really large difference. And that's our model. So this has already been implemented in a few production renderers, and more will be probably coming soon. So it's out there if you want to start playing around with it. And now I'm going to pass it off to Steve, and he's going to discuss the importance sampling for this new model. Thank you.
Okay, I should move this down. So we presented our shading model, looks like this, but it's not enough just to evaluate our shading model in a production path tracer, or increasingly in a real-time renderer where we need to do real-time ray tracing. We need to be able to sample it as well. We might be doing restir for light importance sampling, but often in the mix, there's BSDF importance sampling as well. So we want to be able to efficiently importance sample our shading model, because that will result in better direction sampling, that will result in less noise in our renders. And that's, of course, particularly important with real time, because we can only afford maybe one ray per pixel per frame. So mathematically, this is the kind of sampling we're doing. We're sampling over the upper hemisphere in this case, because it's a BRDF. We've got some lighting. I'm not really going to focus on the lighting part here. We've got our shading model, EON. We've got the clamped projection cosine. And then we've got the sampling PDF of whatever sampling function we're using to importance sample our BRDF. Unfortunately, there isn't a closed form perfect importance sampling scheme for Oren-Nayar or our variants, but I'm going to walk through the steps of getting close to that. The main takeaway with this equation here is just this aggregate here. You can think of as the throughput weight. And the ideal is, if we were doing perfect importance sampling, this would be 1 across all directions. And then that's what we're sort of aiming. That's a sort of North Star. We want to get to that, or as close to that as possible. So let's go back and look at visually at our BRDF. Now, in the simplest case is roughness is 0, where it falls back to Lambertian, just a cosine lobe. And so that's what we're representing here in blue on the left. And we're looking at this at the view angle of 0, normal incidence. And if we look at grazing angles, it's not changing. It's just a constant. There's no view dependence here. But if we look at roughness of 1, things get more interesting. If we go back and forth, we can see at normal incidence, it gets a little bit more peaky. But at grazing angles, it really changes. That lobe is sort of smooshing and rotating over, and we're getting, now this is a sphere lit from the same direction as the view direction, as the viewer. So we're getting more light scattering back towards the viewer, and we can see that there's more light coming back on omega O, our view direction. And so we're getting that flatter result. So that's how visually it's working. Okay, so we want to sample this, and this is the interesting case I'm going to focus on, roughness of 1, and then all other roughness values are sort of like a mix between these two cases. So this is the kind of the most tricky case that we want to sample. So let's do the most basic thing we can, which is uniform sampling. And this is visualized with this green lobe and the sort of radius, well, the sort of length of each of these sample directions is the PDF of our sampling. And we can see there's a lot of noise. This is a sphere rendered in a uniform lighting environment. So all of the noise is coming from our throughput weight. And why is that? It's because, well, these two things are mismatched. You can see that visually with the two sets of lobes. But mathematically, we've got the numerator, which is our target. It's the cosine weighted EON BRDF. And then we've got our sampling PDF on the denominator. And sometimes, when these are out of sync, we're going to get values that are higher or lower than 1. And yeah, I'm just using gray lighting just to sort of show where things are going above mid-gray or below mid-gray. Okay, so can we do a little bit better than this? If we do cosine importance sampling, then we can see we get a lot less noise at normal instance in the center of the sphere. You can see visually it's a pretty good match, a roughness of 1 still. But again, at grazing angles, there's a mismatch, right? It's not adaptive. We've just got this cosine lobe that we're drawing samples from. You can think of it as a sampling proxy. And so can we improve this sampling proxy a bit more? Can we make it more adaptive based on roughness and view angle? And so to do that, we turn to an existing solution. This is linearly transformed cosine. So basically the idea is to take a cosine lobe or a cosine distribution of samples and warp those samples to better fit a target BRDF. And this was used originally in the context of area lighting with GGX, but we're going to use it here to kind of find a good fit of transforms to warp our cosine distribution to better fit EON in this case. So going back, this is cosine sampling again. And if we switch to linearly transformed cosines, you can see it's a much better fit and there's less noise. But there's one problem here. If we zoom into this region of the sphere, we can see there are these black pixels. And these are actually, I'm highlighting them here in orange just in case you can't see. They're not just dark samples, they're completely wasted. They have 0 contribution. So why is that? It's when we draw samples from our cosine, our warped or LTC lobe, there are going to be some directions that end up pointing into the surface. And they will just have 0 contribution because of the clamped cosine term. So they're wasted. And we could choose to generate new samples, but then that, as Chris was mentioning earlier in his talk, then you end up with a difference of work between threads. That's not really efficient. So we'd really like our sampling scheme to just not generate those in the first place. So how can we do that? Well, we looked back at this configuration. We wondered, could we somehow use this plane in the transform space to just reject samples that are going below it? And we have some nice diagram in the paper, but it's a little bit too complicated to go through here because there's a lot of variables and terms. So I'm going to go through in a more intuitive way. At least this is how I think about it. So to actually generate samples for the LTC lobe, one way to do that is to uniformly sample the unit disk. And then you project those samples up onto the upper hemisphere. That gives you actually a cosine distribution shown here. And then we transform those sample directions using the LTC matrix based on roughness and view angle. And we get this transform distribution. Okay. We thought, could we take this plane in transform space and inverse transform it back into the original hemispherical space and then use that somehow? If we look at that, we can see actually what we want to do is to generate samples only in the portion of the upper hemisphere that is in front of this plane. And in 2D, well, you can see then if you go a step back from that even, you want to sample from this region of the unit disk on the plane. So it's a unit disk with a little sort of crescent cut out where we don't want to sample. And this problem was actually solved already in another JCDT paper that was targeting GGX again. It's more complicated than what we need because we're not projecting into an arbitrary view direction. We're just projecting up onto the upper hemisphere. So we don't need all the machinery of this, but it gives us a way to sample that sub-region of the unit disk. So if we go back, we do this sampling of the sub-region, we project up onto the upper hemisphere, we end up with a clipped cosine distribution, and then we transform that as before. and then we end up with no samples going below the horizon. So every sample counts. So here's where we were before, and when we switch to the CLTC sampling, we end up with no wasted samples. There are some dark samples, but they're not wasted, and it may be that they're actually important in real lighting scenarios where we may be having strong lighting at grazing angles, and they will actually have a big impact. There's another problem, and it was present with the other methods as well, is that there can sometimes be these fireflies, high throughput weights. And these are a bit of a problem because they can be sometimes more difficult to denoise. Maybe the denoiser is going to see that as a feature. So we'd like to eliminate that. And we've got some graphs that show that it's a lot noisier than what we'd like to have, a lot noisier actually than cosine importance sampling. So it's not great. What can we do here? And there's another issue that's related to that, is that actually when we apply this transform to the cosine lobe, we get a good fit, but actually down at the base, our EON lobe actually goes behind our LTC lobe. So there are directions that we can't actually sample with our LTC lobe. They're only going to be going kind of in this direction outwards. So we're not going to sample those, and that results in a small amount of bias. It's not really that important perhaps for real-time rendering, but it would be nice if we could eliminate this. So in practice, what we do is we combine CLTC sampling with a little bit of uniform sampling by MIS. And why do we use uniform sampling? Well, it helps. It's just uniformly kind of bad, but the PDF is very stable. And when we combine it with balanced MIS heuristic, then we end up basically with our PDF cannot really go that low. It just helps to avoid these spikes and fireflies. And we vary this probability of uniform sampling based on mu, the cosine of the view angle. And there's an attenuation term based on roughness, because we don't want to do this for all roughness values. As soon as we go to low roughness values, it's just adding variance to use uniform sampling with very little benefit. So we scale it down to zero at zero roughness. And so with that, we end up eliminating our fireflies. There's a little bit more variance, but it's a lot easier to work with and denoise. I should say that all of these renders are done with one sample per pixel to really show the problem. But that's a case that we would have in real time anyway. It's just we would only have one sample per pixel. Of course, we'll use temporal sampling and temporal averaging and denoising on top of this. But it's still important to have good properties with just one sample per pixel, especially when you have things like disocclusion, where we might fall back to this case. So with this MIS approach, we end up with smoother throughput weights, our spikes and fireflies are gone, and our bias is eliminated. So I showed some synthetic renders, but with real path trace results, you can see the benefits of this as well. On the left, we have cosine importance sampling, and on the right, our final importance sampling scheme. And you can see, particularly in the red region, there's a lot less noise. Here's another result. It's a bit more subtle, but there's still some benefits to our approach over the previous method. I should say that cosine sampling is something that's typically the method that's used in production right now. So we're comparing what's kind of the current state of the art versus what we're doing. So in conclusion, we've presented a new energy preserving variant of RNIA, and we've also presented a general importance sampling technique, which we think could be used elsewhere. So future work. As Peter mentioned, RNI uses a V-groove assumption for microfacets. This isn't really aligned with the microfacet assumptions of our specular model in OpenPPR, so it'd be nice to align these. We focus on RNI because it's already used widely in production, and we wanted to improve it for that reason. It's already familiar. But there are other new diffuse models. They have some strengths and some weaknesses. There might be a way to combine some ideas from what we've presented here and that work. But more generally, there isn't really a consensus about what is the best diffuse model. Is it one that spans all of these different types of diffuse surfaces? Is it one that's artist friendly? Is it one that's high performance, one that's energy preserving? It's kind of all of these things, and across different axes. It'd be nice if there was a state-of-the-art report or a survey on the broader range of diffuse shading models out there. So thank you.
Hey, great presentation, great work. I really enjoyed reading your paper earlier. And I don't remember this from reading the paper, and I thought it might be a question that interests others in the audience. When you described this last step of mixing in the uniform distribution, like a form of defensive sampling, basically, did you consider, for example, the cosine lobe? I'm sure you did. Or basically some other distributions that would be kind of, I imagine like maybe cosine distribution is not focused enough on this region, right?
Yeah, if I go back a bit to the cosine comparison, it's going to take a while. Yeah, there are still cases like at grazing angles where actually there can be high variance, worse than uniform sampling. So that's why we picked uniform sampling, because it kind of is still, it's better in that case. So it's kind of addressing particularly the sort of grazing angle cases.
So then I guess like inverse of cosine sampling, right?
Oh, maybe, yeah. Absolutely. That's definitely, we sort of arrived at, we still feel there's room for improvement with what we're doing here, even though if you look at the plots in the paper, I think it's already performing pretty well, and you can see visually it's pretty good on the sphere renders. It's low noise, but I do think we can squeeze out a little bit more. So it might be that. Something else I sort of experimented with but rejected just because I was thinking from my perspective as a real-time renderer, like engineer, is that there is unexplored space of LTCs where you could have a cosine raised to a power, and you could decide to vary that power based on roughness. And that gives you a richer set of kind of lobe shapes. You could probably get a better fit, and maybe you could eliminate this problem and you wouldn't even need MIS. But I didn't want to do that because it doesn't allow the same lobe fit to be used for area lighting. And so I wanted to kind of preserve that as maybe something that could be used for real time. But maybe you want to have one thing that's specialized for importance sampling and another thing that's used for area lighting. And they don't have to be the same. So you could specialize on each of these cases and, in different contexts, use the right solution.
Cool. Thank you again. Awesome work.
Hello. You mentioned this a bit earlier in the important sampling section of it, but I kind of missed what context it was in. Does the important sampling technique used here work with Restir, or does it replace it? Or if it works with Restir, how is that pipeline set up to use both at the same time? Or is it replacing it?
Okay.
Sorry.
I think there's a component of importance sampling. Well, you could consider the SDF in the Restir light selection as well, right? And so they can be compatible. You could combine Restir with multiple importance sampling with your BRDF in sampling. So you can use, depends, there are a range of techniques for combining sampling strategies. And yeah, it may be in the mix and just choosing how because you could do product importance sampling of your lights and your BRDF. It may get expensive to do all those evaluations and so on. So often you tend to use a simpler proxy for things like Restir, I guess. Chris, help me if I'm butchering this.
Well, for paths, we often use BSDF sampling as part of it, so this could be directly used.
Yeah, so that there's not one or the other. In practice, you're combining these techniques.
That's why I thought I just.
So I have one question. You first talked about BRDF, and then at the end you used the term diffuse model. And also that was one thing that struck me, that most of the images you showed were pretty much diffuse. Now, on the other hand, over the last year or so, I've seen a lot of people that used my software and kind of seem to think we need one model and we mess just with a roughness. So there's no real concept of diffuse model versus BRDF, and they just want to say, I just want to use a very, very low roughness, and then it's supposed to be specular. So how does yours work if you try to do that?
Yeah, it's an interesting question. So technically, like I showed at the very beginning, specular reflection and diffuse reflection are coming from different underlying mechanisms. So specular reflection is coming from reflection directly off the surface, diffuse reflection from the body of the material itself. So in practice, they don't necessarily need the same roughness value. In OpenPBR, in fact, we have two separate roughness values. Conceptually, it's nice to have one, but since they're very different effects, it's also possible to have two. And it should be noted that the BRDF, this bidirectional reflectance distribution function, it actually encompasses all these different effects. So the specular and the diffuse can be part of one BRDF. A single BRDF, like the ones we define in OpenPBR, can consist of like many different sliders, many different knobs. So there's many ways of like putting the pieces together, mixing together different effects, but ultimately we come up with one BRDF in the end, and we apply that to the object.
All right, let's thank our speakers one more time. All right, the final talk of this session is going to be a stack-free traversal algorithm for left-balanced KD trees, and Ingo Wall is going to be presenting.
Okay, so my talk is a little bit of an outlier because this is the rendering section, and what I'm doing is not actually rendering. I'm talking about KD trees and KNN or KNN-style queries. Of course, I actually got to use those 30 years ago first for photon mapping, which was kind of rendering, so we'll count that. But I'm not actually talking about rendering per se. So in this talk, I'll first talk a little bit about k-nearest neighbor queries, what they are and why we do them, then what KD trees are and how they come in for KNN queries, then the question of why do we even want to have a stack-free traversal, and then the most part of the talk will actually be about the traversal algorithm itself that we've come up with. So for KNN and similar, and I explicitly say similar because you talk to 20 people that all come to you and say, we want to do KNN queries, and then you start talking to them and you realize you're talking about 20 different things because everyone wants to have it a little bit different. So some of them want to have just the closest point, the other ones have the n closest points, the other one want to have those on the positive hemisphere and whatever. So there's an entire family of methods here that we're talking about. But generally we're talking about a set of points, data points. Those could be coming from a simulation in an HPC code. They could be photons and photon mapping. They could be from a car that has a LiDAR sensor and on the fly generates sensor points. Anything like that, that's the input data points. And then we have another set, one or more so-called query points, and those are the points that we want to answer the question of KNN queries for. And what you want to have, and sometimes they're the same points, and sometimes they're very different. Like they might be on the car that has the LiDAR sensor to realize whether you get close to something, right? But it could also be the same ones. And so for these points, you want, in this case, to have the k equals 3 nearest neighbors. You just want to know for each of these points, what are the nearest points to those with, as I said, sometimes some modifications based on exactly what you're trying to solve. So this immediately leads us to point KD trees, and I explicitly say point KD trees because there's another sort of KD trees which is very different. And this is actually a data structure that has its 50th anniversary this year. So that gives you an idea of how old that stuff is. A point KD tree is a spatial partitioning tree, a binary tree, where unlike other data structures, the points themselves are the partitioning planes and the nodes. So every partitioning plane goes through a point, every point defines a partitioning plane. That makes them a little bit different. And they're very good for these kind of queries. And again, they're not supposed to be confused with the other sort of KD trees that we use in ray tracing. So the reason these kind of KD trees are so often used for KNN queries, and that became probably most famous use in photo mapping when Jensen came out with that, is that if you build them in a very specific way where you have a left balanced binary tree, then you can actually express the entire topology of the tree by just the order of the points in the array. So there's not a single byte of pointer or bounding boxes or anything in there. You just have an array of points, and just the order of the points in this array defines the entire tree, and that makes them very compact, very easy to transmit, and all of those are useful properties. So that's the main reason why people use them for that. I might say a BVH might actually be better, but lots of people, when they think of KNN queries, they think of KD trees, period. So the kind of query that you want to do then on those is think mentally of, you start with a set of the k-nearest points that you've already found while traversing the tree. So you start with an empty set, of course, but that's always have that in your mind. There's a set of k-nearest points that you may have found already, and that defines also some maximum search radius that that might be infinite to start with, but it could also be user provided. And then if you have found a certain number of k points already, then of course you don't have to look for anything further than the furthest of those k, and that kind of starts shrinking the radius. So you always have this kind of set of k nearest points and this maximum search radius, then you traverse that down the tree. Every time you come to a node, that node is both a point and a split plane. So the first thing you do is, okay, I'll take the point associated with this plane. I will see if that belongs into my KNN set, if it's closer than any of the ones I already have, meaning it's within the radius. And if so, I'll add it in this set. That might shrink the radius, or it might have been outside of the radius, and I'll just ignore it. After that, I can say I can take the two half spaces that this plane now defines and classify them into what we call a close child and a far child. The one is the one that has the query point on its side of the plane, and the other one is the obviously other one. So put the query point on the right side of the plane, it would just flip. But those two, like close child and far child, are very well defined by just the point, the plane, and the query point. So that's a very clear thing. So you've already processed your point n. So now you go first into the close child, recurse into that one, and try to shrink that radius even more and finding more points. And when you come back from that, you will see if your query radius still overlaps that plane, meaning the far child still could have any other kind of points contributing to that. And if so, you also recurse into the far child, right? Very easy. In the other case, if the close child has already shrunk that radius so much that the radius is smaller than the distance of the point to the plane, then we can skip the far child and just go back to the parent. So yeah, at the end, we go back to the parent, done. Very simple algorithm that's already in the photo mapping paper in the first one, very easy to code down. The easiest way to code that down is actually in a real recursive algorithm. It's literally like 5 lines of code. It's so simple. And on a CPU, that's actually not too horrible. Function calls aren't good, but at the same time, all of that stuff ends up in the stack. The stack fits in cache, caches are fast, so it's okay, right? If you just want to have something fast written down quickly, then that's the way to go, right? If you want to have it a little bit faster, and in particular, if you have a architecture where you don't want to have any actual function calls, then what you typically do is you use a software managed stack where you keep an array of not yet traversed nodes, and then you always push to this thing or pop from this thing and iterate over that in a loop. And that is also great. The only problem with that is if you run that on a GPU, or even worse, if you wanted to build hardware for that, you would quickly realize that you have order 50,000 threads running on a modern GPU. And these 50,000 threads each have their own stack because, of course, they have to be different stacks for every thread. Each of these stacks needs reading from and often writing to in every iteration of this thing. Those are indirect accesses, so they also go to gmem and not into kind of registers or something. It's far too much memory traffic to go into cache, so you'll have a lot of memory operations in every iteration of this thing. So that is kind of a problem. And then there's also software engineering problems. If you have that in a small function in a library that gets called by other things, then you start messing up their memory management. And so it's kind of nasty. So you would ideally want to have something that doesn't need an actual stack. So there has actually been an entire litany of papers that looked at stack-free traversal methods for KD trees, the other KD trees. 2 of those actually at I3D, which I didn't even realize until I made this slide. So there's some work that looked at that in the past. The problem is that was for the different style of KD trees. So they don't actually work that well because it's really a very different style of KD tree. You probably don't want to use that for KNN queries. And the other problem is therefore ray tracing, which is a very different sort of query because you traverse along a line. So there's always an obvious like next behind the current leaf that I've left. And for the kind of queries you want to do that is not the case. So most of these don't apply. We had a different paper, Hapala, I, and a few others in 2011 for BVHs that used a stack machine approach. And what I'm describing here is very similar to that. It's just in a slightly different context, which actually makes many things much easier. So let's try to come up with an algorithm that we can traverse this thing and do a KNN style query with. So assume we have this one-dimensional KD tree in the proper ordering, properly left balanced, etc. So assume we have that, and assume we want to do a for illustration purposes, a 1D query at this query point where the sun happens in the slides, and with this radius, this white radius that we want to query with. So if we were to start with that, we start at the root, we then go, we process the root, of course, and then we go to the closed child, which is 1. And then from 1, we do the same, we process 1, we go to the closed child, and again and again. At some point, we start returning from this recursion, and we come back to 4. And now at 4, we say, okay, we just came back from the closed child, we're still in radius, so we'll go to the far child, etc., etc., etc. Right? We go back, and this goes on and on and on. This is how traversal of a KD tree works if you were to implement it purely recursively. Now let's look at one of these nodes, the 1 link coming in and the 2 links going out, and also see how the traversal happened with these arrows. We can now make a few observations of what actually happens in this traversal. The first, most important one is each node can get visited and often does get visited exactly or up to 3 times. There's no other cases. You can only ever come to a single node in 3 different ways. The first and most obvious one is when you come from the parent and go down and first come to this node. If that happens, we will process this node, see if it belongs into the query set, shrink the radius if necessary, etc., etc. And after that, we will always go to the closed child, which is a very well-defined thing at this point. If that child exists, so ignore that part. I'll come back to this later. But this is a very clear thing, right? I mean, this is the main thing. You come for the first time from the parent, then you process the node, and then you go to the closed child. The second case, how you could possibly come to a node, is if you were in the closed child and you come back from the recursion and you come back to this node. In this case, you don't have to process the node again. You've already done it, but you have to compare to the distance and see if you want to go to the far child, and if so, go to the far child or skip it. And the third case that can possibly happen is if we had been at the far child, assuming it existed and was in the radius, and etc., etc., and then we come back to that, and then we say, okay, we're done with this node, and back up in the recursion. So that's the only 3 cases that we have. And if you look at this now from kind of like a rules and state kind of mindset, you see we have 3 different possible conditions that lead to 3 different states, and then these 3 states tell you what kind of next thing to do. So the conditions for these 3 states, they all involved if coming from. And they were only if coming from parent, from near, or from far. That's the only 3 things that matter. So all we need to evaluate these kind of 3 rules and figure out which state we are actually in is what node am I currently at, and what state, which node was I in the last traversal set. That's the only 2 values I need to know which of these 3 states I'm in. Now, for each of these states, we also have this set of rules of what to do. Like, do we need to process the node itself? Yeah, only if we came from the parent. Very simple thing, right? And similarly, these rules tell us which node the traversal would want to go next. So we have the current node, the previous node, and now we also have a next node. And then you can see that as a state machine, which kind of like just defines which state you're in and which arrows, which rules to follow and what to happen. And the state transition is then very simple. The current node becomes the last node, the previous node, and the next node becomes the current node. And then we just iterate. So very, very simple thing. There is, and you can actually code it up this way. That was the first way it was coded. You can actually even simplify that a little bit more, because there were all these kind of like, if that child exists, and if not, then that, and if that one also doesn't exist, then maybe that, and that becomes a little bit tricky to code. But what you can also do is you can simplify these expressions where I said, if it exists, and just say, in the space of the KD tree, in the space of possible node IDs, the children always exist, right? The node itself might not exist if the array isn't that large, so I can easily figure out whether a given child does or does not exist. It's either an ID behind the size of the array or it's in the array. But I can always say the left child ID or the closed child ID of this and that ID is this, and the far child ID is that. So if we do that, we can always just say, okay, we just compute the child IDs, we just set the next value to that, we go to this child, and then the first time we come to a child, we say like, it doesn't actually exist, let's just back off. And if we do that, then the algorithm becomes much, much, much simpler, right? So that's the main thing. You can get rid of the first 2 of these exists. The same thing, the only case that we can ever go to a parent that does not exist is if we're at the root node Our next node to traverse to is -1, which is if you plug in the formula, the root of 0, the parent of 0, and that is, if that happens, we're done. So also nothing special to do, so we can also pretty much ignore that. So we end up with some very simple rules. We start our state machine by saying the current node is 0, which is the root node, and we say the previous node is the parent ID of function of 0, which is -1. And then we start iterating this thing. And in this traversal, first thing, we do this hacky thing. We say we check if the current node ID is invalid. And if so, don't do anything, just sit next to the parent and done, right? Very easy thing. And everything else will then fall into place. If that didn't happen, then we check if we came from the parent, right? Very simple thing to evaluate. And if so, we process the node, whatever that might mean, and then we sit next to near child. If that didn't apply, we check if we came from the far child, and if the far child is also in range. If so, we set it to far. We came from the near child, and far child is in range. If so, we go to the far side. If neither of these things applied, then the only two possibilities are either the far child is not in range, or we came back from the far child, which means we go to the parent. That's it. And then the only other hacky thing is if the next node ID that we just computed is -1, bail out. We're done. So the entire code is literally only one page of CUDA code, and I would say at least half of that code is comments, which I don't write usually that much of, but in that case, it's really, really a small piece of code. So very easy to code. There's reference code for that available on a GitHub repo of mine. You can do with it whatever you like. It also has a GPU side KD tree builder, which is also published at JCGT. It also has some other traversal techniques, which actually for some point distributions are way, way, way better and faster, which aren't published yet. But all of the code is in there. The entire code in that repo is written as what I call traversal templates. So that function you've just seen is really just traversing the tree. It's not saying what to do once you reach a point. It's all templated over a Lambda function. You provide the Lambda function, and you can do in there whatever you want. So do your KNN query, do a find closest point, do whatever you want. Very powerful statement that you can actually express this traversal without having to know what to do. And similarly, this entire code is even templated over the dimensionality and over what is a point and all these kind of things. I have some reference results for that, though, as I said, the point was not to have the fastest possible query for a specific kind of KNN query or a specific K. So this is just a set of different experiments I run for making sure that everything is right and making sure that the performance numbers look reasonable. All of that said, might I suggest, if you want to do these kind of queries, to also look at BVHs. I have a different library for that, and for many things, the BVHs are better. I just have to maintain this repo because the first thing that everybody looks at is KD trees. So still, might I suggest looking at BVHs and not actually using that? But if you want to use KD trees for the compactness and the transferability and all these other reasons, this is an interesting thing. So with that, any questions?
So you're suggesting using BVHs rather than KNNs. Do you mean then using left balanced BVHs and using the same algorithm?
No.
Or just...
No. BVHs are a totally different kind of animal because just like the ray tracing KD trees, there are different trees where you have a distinct difference between inner nodes and leaf nodes. So both in the ray tracing KD trees, like not mine, but the ray tracing KD trees and the BVHs, you have inner nodes that have some kind of bounding information and that point to children. At some point, you have leaves and they contain multiple different primitives. And so you can't actually well, you probably could, but it doesn't make sense to left balance them. It just doesn't make sense. You really want to have them unbalanced, actually, for a variety of reasons. So the main reason I would suggest BVHs is that they are similarly compact if you have multiple points together in a leaf, which typically you want to have anyway. And the other thing is you can put data other than points in. Point KD trees work for points, right? And nothing else, because it implies that this plane goes through this point and the point does not stick out on either side of the plane. So you cannot use it for triangles. Now, many of the queries that I'm getting recently that people ask me about is, some call it wall queries, right? Which is, find me the closest point on the simulation domain of some triangular surface on an airplane wing or something. Those are triangles, those are not points. I can't actually use KD trees for that. Or kind of side distance functions, these kind of things. They typically operate on triangles or splats or whatever else. And so for that reason alone, I would suggest BVHs. The main advantage of KD trees is really this kind of compactness thing. You don't have to rebuild much or something. You just, once you have this array, you save it and you reuse it, send it around, whatever. That is useful, but the generality of a BVH is just so much higher.
Other questions?
Hi, thank you. It was a really interesting talk. So you said it works for points. Does it work for spheres or disks? That's question number one. And question number two, can you talk a little bit about the performance again? Because does it say what's the performance in terms of like constructing the tree versus like constructing the BVH every frame or something like that? And what is the performance in terms of inference, say if you're just, having a query?
That's a lot of questions that we could talk about 2 hours for. So first of all, the BVH construction was not part of this paper, but I have one. There's one in this repo, and there's even a JCGT paper about it. It's GPU. You can do it on a GPU. It's fairly decently fast. I've not yet heard anybody complain about the aspect of that. Typically, the query times are much, much higher than the build times for the kind of users I had. BVHs should be equally fast, but I haven't done and I'm talking order of magnitude. I have absolutely not run the numbers. So for my BVH library, I have different builders. I have one that is super, super fast. I would expect that to be faster than the KD tree builder, but I've never measured it. And then there's a few others which are more stable with respect to crazy input things where you have like outliers or something. In terms of query, that is actually an interesting thing because most people, including me, measure KNN queries on random distributions or semi-uniform distributions, like photons on a surface, which are often kind of reasonably well uniformly distributed. What I found over the last few years, and I have the numbers for that, I've just never written it up, is that the kind of query just described, which is what people use for 50 years now, actually can go horribly wrong if you have queries and data points distributions that do not match well. That is because you always compare distance to a plane, but if your point is more diagonally away from a huge cluster, then you can actually end up with like an entire subtree of tens of thousands of points, none of which will ever trigger any of the culling things to the plane because diagonal is a different weight metric than projected, right? A BVH will not have this problem. I have a query for KD trees that also fixes that, but that is not in these numbers that I have just described because you have to modify this algorithm a little bit to do this kind of what I call closest corner tracking. You can do that, but I didn't want to go into that in the talk.
So like to summarize, is it like interactive if you're like doing a simulation? Like if you just every
yeah, sure.
Okay.
I mean, the numbers I had queries is like, was the closest point, sure, there's only the closest point is a few billion queries per second.
Okay.
KNN is, what is that like? Oh, God, my eyes. Like a few 100 million queries per second. And that is on a 3090 Ti, which we just learned today is even low-end hardware. I wouldn't, for that kind of, like for a sensor in a car or something, I wouldn't be worried too much.
Sure. Thank you.
So all of these numbers are for your method, but did you do any comparison to the standard stackful traversal for KD tree?
Yes, but they're not in the paper. No, I mean, this repo has 4 or 5 different traversal methods, and of course it has the stack-based method. It has the stack-based method, it has the stack-based method with closest corner tracking, it has this one with closest corner tracking, and 2 or 3 more. I'm not, I mean, the only thing I can say, I'm not claiming that this is the fastest method. I'm not claiming that this is faster, always faster than the stack. Actually, in some cases, the stack may be faster. It depends on so many different things. But what I realized is that how should I say that? If you really just do K and N queries, if that's the only thing your kernel does, points in, KD3 in, query, done, return, right? Then maybe the stack is not such a bad thing. If you want to take the same thing and put it into a shader in DXR or in optics or something like that, and suddenly your shader that assumes that it has a fixed set of registers or something is starting to doing crazy things with like lists of 50 photons and doing whatever in there, then you start messing with lots of other things where it's hard to define. It's more of a software practice, kind of being a good citizen of not defining your own giant stack somewhere in a function that somebody else might call and not even know about. That is the main reason why, if or when I use that technique, it's really just, I want to make sure that I'm not messing with anybody else. I'll use that. It might be 10% slower. I don't know. Yes, I have measured, but I can't remember the numbers. But it's not going to be like orders of magnitude difference. Certainly not.
That's fair. Thanks.
All right, we should probably end here and you can go and take other questions offline.